Hi there, and welcome to Chapter 1.3 from Stevens' Matrices, Vectors, and 3D Math. In this chapter, we're going to be discussing inverses and determinants of matrices. Right? And these will help us determine whether or not we can solve a system of linear equations. Okay, we'll tell us some other things too, but with respect to what we're doing in Chapters 1.1 and 1.2, that seems to be the most pertinent at the time. And let me just give a little preview in terms of standard algebra that you may have taken in high school. If you look at this equation, ax equals b, right? I'll put it over here. X equals b, and I say solve for x, right? Where a is just a number and b is just a number. Most people would just say, all right, x equals b over a. And the real conscientious students would say, provided a does not equal 0. Right? And that's pretty important, you know. But it's pretty easy for us to look at a number and determine whether or not it is 0. So in matrix algebra, we have a similar situation, right? If we just change this to a capital A, and that's now a matrix, we would like to do something like x equals, and get it like that. So we have no x's on the right-hand side. But the problem is, we can only do that if this A, if this was, one-dimensional algebra, if that A was not 0. But now I'm dealing with a matrix. But we do have something similar to a 0 in this form, but it's not the actual 0 matrix. We need to know whether or not A has an inverse, right? And the reason, and you may have seen this before, if you had something like 3x equals 6, you're able to solve that because 3 has an inverse. 1/3 is the multiplicative inverse. So if I multiply both sides of that equation by the inverse of 3, I get x equals 2. So we're going to do that same kind of game here, only we're looking for the inverse of a matrix. Okay, and then we will look at the determinant, which is sort of telling us whether or not this matrix has an inverse. Okay, so moving on, let me go into full screen mode for this. Okay, good. So we're going to define what the inverse of a matrix is, and just like before we had the inverse of 3 was 1/3. That's because when you took 1/3 times 3, that equals 1. So we're going to define the inverse of a matrix in a similar form, only we don't have 1, we have the identity matrix, which is sort of the 1 of matrices. So if we have a square matrix A, and then if there exists another matrix B, so that A times B equals B times A equals the identity matrix, then we call this B the inverse of A. Right? Basically what that means is when we take A times B, we get the identity matrix. And so instead of calling it B, we call it A inverse. So A times A inverse will equal the identity matrix. Right? And likewise, you can switch the order in this type of situation. A inverse times A had better also give you the identity matrix of the appropriate size. Okay, if A has an inverse, it's called invertible. If it is invertible, it's also called non-singular. If there is no inverse, if A has no inverse, it's called singular. And I use all of these terms, so the actual terminology isn't that important, except that these terms get used throughout the rest of the chapter, so it's worth knowing that. So, invertible, non-singular. No inverse, singular. Okay, and so you can figure out a formula for the inverse of a 2 by 2. All right, that's my 2 by 2 matrix, where A, B, C, and D are just numbers. Then I need to find, A, B, C, D. I need to figure out what this matrix is, X, Y, Z, W. This is my unknown. It has to give me 1, 0, 0, 1. And if you solve that, it actually results in 4 equations and 4 unknowns, these 4 unknowns here. And it takes quite a while, but you can come up with a formula for what this matrix is. That's the inverse of my 2 by 2. And so when you do that, you get this form of the inverse for a 2 by 2 matrix. So it looks like this. There's a number out in front. This is just a scalar. And it's 1 over, I'll do it like this, AD, right, minus B times C. Right, so I get that number out front. And then the matrix looks pretty similar, except that these two get switched, A and D get switched, and B and C get negated. Right? It's not that hard to remember after you do it a few times. It is sort of worth having this in memory because we will be doing it enough. You might not want to have to look for the formula every time. Okay, so one thing that should be noted here is that if you look at this inverse, all right, and we look at this bottom, the denominator of this fraction, that is just a number, and you're dividing by that number, so that number better not be 0. AD minus BC can't be 0. If it is, you have no matrix, you have no inverse, right? And so that number, AD minus BC, is called the determinant of this 2 by 2 matrix, because it determines whether or not there is an inverse. And the nice thing about this is that now we can, if we know we have an inverse, and we won't always, but if we do know we have an inverse and we have this matrix equation, then I can symbolically write the solution to that equation as x equals A inverse times B. And that's basically done through a little sequence of operations here. If I multiply on the left by A inverse, then what I have here is the identity matrix. But the identity matrix multiplied by any matrix or vector just returns that vector. So I just get x equals A inverse B. Right? So now it's really simple to get a solution. Symbolically, there's still some work because you have to figure out what that inverse is, and that's sort of a mess. But at least we can write this solution in closed form. Okay, so if we take a look at our little example here, suppose we have a system of equations that looks like this. Right? If we write that as AX equals B, then A is just the coefficient matrix, 1, 2, 3, 4. X is we'll call them x1 and x2 equals 5, 6. Right? So I can get the solution. I can get x by x equals A inverse B. Right? And so that's all I'm doing here. X equals A inverse times B. And now here's that inverse. A inverse is right here. Notice we start with A here. And we're going to switch these two. So I get a 4 and a 1, and I'm going to negate these two. So that's the matrix part. But then I have to divide by, I have to multiply that by a number, which is 1 over the determinant, which is 1 times 4 minus 2 times 3. Right? So that's just 4 minus 6. Right? So that's a negative 2. So instead of putting a negative in the bottom, I get negative 1/2. So there's my A inverse. And there's B. And so I can simplify this. The first thing I'll do is do this multiplication here, and it'll result in this. So that's going to be 4 times 5, which is 20, minus 2 times 6, which is 12, so I get an 8. All right. And then my second term, negative 3 times 5 is negative 15, plus 1 times 6, which is negative 9. All right? But I still have my 1/2, my negative 1/2 sitting out in front of there. So when I do my scalar multiplication, that becomes a negative 4. That becomes a 4.5. Right? So I get a solution. Right? And this will be extra friendly whenever I have a computer do this for me. Right? So is that an actual solution? Well, sure. We can actually just check. If we let x1 be negative 4 and x2 be 4.5, and I plug those values into these two equations, right? Those are my original two equations. I get negative 4 plus 2 times 4.5, which is negative 4 plus 9 is 5. And then whenever I plug in x1 and x2, simplify, I get 6. So when I plug in those answers found by A inverse B, I get solution to my system, right? So we start off with the system, convert it to a matrix equation, get the inverse of the coefficient matrix, and we can get the solution quite easily. Okay, notice that was without any Gaussian elimination or row reduction as we did it in the last chapter. Okay, so I'll do a couple of inverse theorems, and then we'll get into finding the inverse of a larger matrix. So here are the inverse theorems. There is a little, this is not quite as you might expect. Remember in regular 1D algebra, if you had a times b to the x, that would give you a to the x, b to the x. That doesn't quite hold here, right? Because the order of operations, or the order in which you multiply matrices does matter. So notice if you take AB inverse, you actually get B inverse A inverse. And that's because in order to get the inverse of AB, I have to multiply by A inverse here to get the identity, and then B inverse there. So that is the actual inverse of AB. The A and the B, the matrices get switched in order. And as you might guess, the inverse of the inverse is the original matrix. The inverse of the transpose is the same thing as the transpose of the inverse. And if you take the inverse of a scalar multiple, right, where you're multiplying a scalar k, or number k, times the matrix A, well, it's just the inverse of the number, which we did at the very beginning here, is just 1 over k, times the inverse of the matrix. And all this stuff is handy when we start solving, things like ax plus b equals cx minus y. If we want to solve for x, these types of things will play a big role, right? These properties. Okay, so I'm not really going to prove them. We'll demonstrate their proof with some MATLAB exercises. So now the next big thing is, so we got an inverse for a 2 by 2, right? If we take the inverse of that, we got 1 over AD minus BC times DA negative B negative C. That's great for a 2 by 2, but what if we have a larger matrix, right? It's defined by the same process, right? The inverse of a matrix, which we'll call X. Suppose we have a matrix A. Its inverse will be such that we get the A times that inverse gives me the identity matrix. So we can actually solve this as a sequence of equations, or a system of equations, where we want to know what we multiply A by to get the identity matrix. So we actually solve this sequence. It's actually a system. It's 3 systems of equations, right? There's the system of equations that gives me this column, a system of equations that gives me this column, and a system of equations that gives me this column. And if you don't quite get that, that's all right. The trick to getting this inverse is to start off with the matrix A here, start off with the identity matrix here, and then row reduce this matrix until it looks like the identity matrix. Doing all the row operations the whole way across, and then what you get over here is actually the inverse. So if we do our row operations to get us there, the first thing we want is a 1 here. We got that, so we don't have to worry about it. So then we want to get a 0 here. So we have to take -4 times this first row and add it to the second. So -4 times 1 is 4. -4 plus 4 is 0. That's why we chose that multiplier. 2 times -4 is -8 plus 9 is 1. 3 times -4 is -12 plus 12 is 0. 1 times -4 is -4 plus 0 is -4. And nothing's going to change here because I have zeros. All right. So the next thing I want to do is get rid of this 2. All right. So I'm going to have to multiply this first row by -2 and add it to the third row. When we do that, I have -2 times 1 gives me -2 plus 2 is 0. That's why we chose that multiplier. 2 times -2 is -4 plus 7 is 3. 3 times -2 is -6 plus 5 is -1. 1 times -2 is -2 plus 0 is -2. And since we have zeros here, we multiply that by -2 and add them. It does not change the last 2. All right, so we're getting there. We have a 1 with zeros below it. Now we want to get a 1 here. That's good. It's already there. I don't have to worry about it. I want this 3 to be a 0. So I multiply this second row by -3. Add it to the third row. -3 times 1 is -3 plus 3 is 0, which is why I use -3 as my multiplier. 0 times -3 is 0 plus -1 is just -1. Nothing happens there. -4 times -3 is 12 plus -2 is 10. 1 times -3 is -3 plus 0 is -3. And 0 times -3 plus 1 is just 1. All right, so I almost have row echelon form. I just have to multiply the third row by -1 so that I get a 1 in that last position. When I do that, my augmented matrix looks like this. It's sort of a super augmented or an augmented matrix. Okay, so now I want to work my way back up. All right, so I'm going to go up and to the left as opposed to down and to the right. All right. So I want a 1 here. Got it. I want a 0 here. Got it. I need to get a 0 here. So I'm going to take -3 times my last row, my third row, and add it to the first. So when I take -3 times 1, I get -3 plus 3 is 0. That's why I use that multiplier. But now I have to go the whole way across the row. -10 times -3 is 30, plus 1 is 31. 3 times -3 is -9, plus 0 is -9. -1 times -3 is 3, plus 0 is 3. And I'm getting there. Things are looking pretty good. So I have a 1 here. 0 is below it. Now I need to get a 1 here. That already happened on our first pass. So I just want to get rid of that 2. I want to make that 2 a 0. So I'm going to take -2 times my second row, add it to my first. So -2 times 1 is -2 plus 2 is 0. Right? That's why I chose the -2. 0 times -2 plus 0 is 0. -4 times -2 is 8 plus 31 is 39. 1 times -2 is -2 plus -9 is -11. 0 times -2 is 0 plus 3 is 3. And again, you don't really have to worry about this term here because it's a 0, but if I take 0 times -2 and add it to 1, I get 1. right? And lo and behold, what I have here is my inverse matrix. Right? That is A inverse. It's a long process. We will, you won't have to do more than one or two of these by hand. We'll actually have MATLAB be doing this for us usually, provided there is an inverse, and there is a way to determine that pretty quickly. Okay, so you know what we'll do? Just to keep this short, we'll start a second video for determinants, right? Here we're going to do determinants in video number 2. So we'll stop here and go into determinants in the next video. All right? Bye.